So with these experiments, I was playing around with these things on a whim, testing hypotheses. My hypotheses, initial ones, ended up being correct. My later hypotheses ended up not being correct. And so now I'm at a point with this particular experiment where I can prove some really cool scientific things, but I can't move this experiment past the needle where I'm at the moment. So let me outline everything that I have here for you, and maybe, hopefully, somebody might want to take this up, or someone at least finds this particular experiment interesting. So with the double slit experiment, the double slit experiment has always interested and fascinated me. It's a very simplistic experiment. Anyone can replicate it. It's what I love about it, right? Like you can replicate it with a piece of construction paper, a flashlight, and like some smoke. Whatever you want to do to generate the smoke. That's literally all you need, right? And then within that, you can generate and replicate and view quantum mechanics like for yourself. Like you can do the experiment. You flash the flashlight. If you watch it, it's going to go through one slit. If you don't watch it, it's going to be a pseudo random pattern through both splits. And then that's where my focus comes in for these experiments, right? Because my hypothesis, as I go through these things, and as I kind of learn more and more about these things, like breaking them down, I think that there's a missing element within this, and that it's not actually random. I think that there's a pattern within quantum mechanics, period, right? I think quantum mechanics is pseudo-random, and I think that we zoom in too much on it, right? Like if we look at it from a zoomed in dimension, it's random, but if you zoom out, then it's not. It's how a lot of things work. And then so I want to take that philosophy and let's experiment with it, right? Let's make this experiment bigger. So that's what I do here. And then so I took an explanation for this particular notebook from ChatGPT, and I just pasted it in here for you, just like for anyone that wants it. So I took like my experiments that I did with this were actually a lot. Like this is this one. It's my like experiments notebook, like my like where I went through and I ran like all these experiments in order, right? And I didn't like so this is just a ton too much, and then so I consolidated them, right? And then so this is what we have here, and this is I'm calling it the 100-slit experiment. And then so essentially what I'm doing is let's break this notebook down into sections, right? And I'll talk about this first section. So this first section is simulating quantum interference patterns, and the first three sections generate interference patterns for the double slit experiment, and then I do 5 slits and 100 slits, right? Why not? So these sections simulate the wave behavior of photons or other particles passing through slits and forming interference patterns. The intensity of the light at different points on the screen is calculated using an equation where the phase shift is dependent on the distance from the slits. And then so let's take a look at this and let's look at our experiments, right? So double slit experiment, this is what you get like a traditional result of the double slit, right? And then so you can see this, and the pattern is it forms a wave pattern, first of all, and it's a pseudo random as to like kind of what this looks like, right? But take it a step further, right? So this is 2 slits, and we know what happens with 2 slits, what happens with 5 slits. Interesting, right? The pattern changes. So it's no longer just a wave, but we see that there are repeats in this pattern. Like it's definitively a repeating pattern. And then so let's take it a step further. What happens if we zoomed out to 100 slits? The shape changes again, right? So this is a completely different shape than this, and this is a completely different shape than this. If you look at this compared to this, you're going to draw completely different conclusions. You're going to draw like 2 different, like very vastly different conclusions, right? And then this too, right? Like you would draw vastly different conclusions from this as opposed to this. And then so all of this is important within this, right? This is all the same thing. We're looking at the same phenomenon here. It's just different shapes. And so I want to highlight and point that out to you, first of all, right? So that's what we're looking at. So when we look at this, and then what we think of as this double slit experiment, and we think of as this beautiful wave, is not. It's this. It's also this. It's different shapes, right? So we have to, number one, the shape and what is going on within these slit experiments varies depending on the dimensionality of it. So we can prove that out. Second thing that I want to prove out within this is I do essentially a couple things within this, right? Let's go to the top here, and then we'll So first thing I'm doing is, second thing I'm doing here is introducing a quantum measurement and uncertainty model. And then so this section introduces a probabilistic AI model to simulate quantum superposition and measurement collapse. It introduces a quantum uncertainty model class. So it initializes with a 50-50 probability distribution mimicking quantum superposition. I use Monte Carlo sampling to simulate the measurement collapse. And then I introduce distillation learning, where each successive student models the refined probability distribution. So I do a lot within this one cell, right? But this is exploring whether or not quantum probabilities can be learned and refined, and whether or not the AI can progressively improve measurement predictions based on previously observed probabilities. So, like I said, I have this other notebook that I'm consolidating, right? And so I'm consolidating like a lot of experiments into one with this particular experiment here. Just because I want, like, so this proves out a few different things here for you, right? The first one is that, so I want to simulate quantum collapse, and that's what I'm doing here, right? And so that's what we do, and that's our end result when we do this, is it's essentially a virtually even probability distribution, but this probability distribution updates and changes, right? It's not 100% constant, but it's virtually even. Like, it's going to be virtually even no matter what, every single time, right? And so that's pretty cool overall. And then so we can measure and impact that. But then the second thing that I'm doing is I'm then taking these probability distributions, and then I'm training a model on the probability distributions, and then distilling that data from the teacher model, and then distilling that into a student model. And I do that 3 times. And then I essentially have the end result that we're looking at here is the distilled predictions that each one of these individual daisy chain models is doing. And then they're all converging around 50%, like 50, right? Which is perfect. That's exactly what we want. This convergence means that they're all training off of something. They're measuring something. What they're measuring in here, I can't tell you. But what I can tell you is that this is not a random pattern. This is not a random pattern. And that these models that I'm training off of these pseudo-random patterns are detecting something. They're detecting a shape in there. They're doing something with it. What they're doing in there, I don't know, man. I can tell you that they're doing something, right? And then so how do I know this? How can I take it a step further? Because I can control that. I can pull the lever here, right? Like, so this is that, like, the lever to control their probability, right? Like what they're predicting here, like, and this collapse, like, and the collapse, like, can I essentially, like, stabilize that collapse? Like, we know that these are the outcomes, right? So this is going to be the pattern. This is going to be the pattern. Can I move it like a lever? Can I change it? Can I change, like, this probability distribution, like, and make it so that it doesn't, like, it's not going to be this wave. I'll just change the shape of it, right? And so that's what I'm testing here, and yeah, I can do that, right? That's what we're seeing. So the blue is like what would be like the standard wave, right? That standard wave that comes about, and then I'm essentially using an AI model and training AI models to predict and then stabilize that wave, right? Like, I want to fix the wave. I want it to not be a random pattern, and then that's what we're seeing, right? So I'm bending it down, and I can essentially fix it and stabilize it, is what we're seeing here. And then so that's where I end with my full experimentation with this, right? And then so based off of all of this, all of these experimentations, I put this together, and this is like the ultimate model, right? This is like, so this is essentially all of my hypotheses around this entire thing combined, right? And a lot of it boils down to this. So let me explain what's going on here. So at this point, what my prediction and my hypothesis is that, like, how quantum mechanics is governed is that it's based off of multi-dimensionality, and each kind of, like, aspect of quantum mechanics is a different dimension of quantum mechanics, right? So we have phase shifts, entanglements, spin coupling, non-local effects, time evolution, tunneling probability, energy distribution, observer interaction, collapsible reversibility, collapse decay, chaos intensity, feedback strength, coherence preservation, and phase synchronization, sync layers, and base frequency. So all of these are aspects and components of quantum mechanics, right? My hypothesis is overall at this point with all of this that all of these individual aspects of quantum mechanics are just a dimension of quantum mechanics, like a individual signal, a node. And then so if you have enough of these nodes, like if I give a model enough dimensions of a quantum phenomenon, if I give it the here's the multi-slit data, here's the entanglement data, here's the spin related data, here's the non-local quantum state data, that with enough of that signal, then it's like, oh, okay, here's the shape, here's the quantum shape. And my hypothesis is that once it does all of that, and we do all of that, and we figure all of that out, we figure out it's all like kind of the same thing, right? That is my larger hypothesis flat out within this, is that like analog and digital, quantum and classical, etc., it's all like the same road, like it's a circle. It's all just like different points on the circle. They're all the same thing overall. And then so I run this, and I can get this to run in its current state here for it runs like, it takes like 45 minutes to run, and then it airs. And then so that's fully where I'm at with what we're looking at here. But I give you also to another flat out, here's a breakdown of this model, right? So this is an AI-driven qubit stabilization in a multi-layer synchronized quantum model. It's the full model. The experiment aims to simulate a multi-layer quantum system with phase synchronization, entanglement, and tunneling effects while using an AI-driven recurrent neural network or an RNN to stabilize the system overall. That's my hypothesis, right? Give it all these variables, we make it play, we won't get quantum collapse. AI model will dynamically adjust a control parameter base frequency to optimize quantum behavior over time. Here's exactly what it's going. Here's all the training mechanisms. And then so this experiment merges quantum system simulation, noise modeling, and AI-based real-time control to investigate whether machine learning can enhance quantum stability. If successful, this could have implications for error correction in quantum computing and AI-driven quantum control systems. I'm probably not going to finish this. I'm just putting it out, and that's why I'm making this video here and now. I don't want to run through and wait 45 minutes for this every single time to debug. At this point is where I'm at with this model. I've proven enough of this overall concept to me. My overall hypothesis that I went into it was this, right? Was that there's a differentiation between this and this. I'm happy. I've proven this to myself. I have the data from these experiments that I need for myself to move forward with regards towards my experimentations within quantum mechanics. So if you have seen this and you want to take this forward, do whatever you want with these experiments. If you do anything with it, please let me know if you do. It'd be super cool. That's the only thing I would ask. But do whatever you want with this code. If you like this type of content, please like and subscribe. Thank you very much.